This lesson is on the sum and difference identities for the cosine function. Before you do this lesson, you should already be familiar with the fundamental identities of trigonometry and also the values of our special angles like 30 degrees, 60 degrees, 45 degrees, and also be able to think about those same angles in terms of radian measure rather than degree measure. To get us started on this lesson, I want us to look at a problem and just help us to realize something that we may not do when we're working with the cosine function. I've written here the cosine of 30 degrees plus 60 degrees. Now you'll notice this 30 degrees plus 60 degrees is inside the parenthesis. So this would indicate that we would add these together and then we would do the cosine of that result. So let's follow that procedure and look at this. 30 degrees plus 60 degrees is 90 degrees. And what is the cosine of 90 degrees? One way that I remember that is to think about the cosine graph. Of course, 90 degrees is just like pi over 2. And we know that at pi over 2, the cosine graph is crossing the x-axis. And so that value is 0, isn't it? Okay? Now, let's look at this other problem down here. We have the cosine of 30 degrees plus the cosine of 60 degrees. Now you'll notice here we're doing the cosines first and then we're adding. Well, the cosine of 30 degrees is square root 3 over 2, and the cosine of 60 degrees is 1/2. And of course those have a common denominator, so we can add square root 3 plus 1 all divided by 2. Now what I wanted you to see here is that this is different from this. Did we get the same answer? These are not equal, are they? That's very important because students very often want to take an expression like this, where you've got a sum of two quantities inside your parenthesis where the cosine function is operating, and they'll want to write this. Now, with the numbers, perhaps you wouldn't be tempted to do that, but in particular, if we have the cosine of a plus b, you'll notice here I'm just using letters instead of these angles. This is not the same as the cosine of a plus the cosine of b. You can see here that using 30 and 60 we've shown that this is not true. So you never ever want to make that assumption. Now I'm assuming that in your trig class your instructor will develop this identity for you, but I have just printed it up here. And we're not going to prove this identity, but what we want to do is to learn this identity and then see how we can work with it and use it as we're working problems. Let's look at, first of all, the identity for the cosine of a sum of two angles or numbers. The cosine of a plus b is equal to the cosine of a times the cosine of b minus the sine of a times the sine of b. Now, you'll notice here that you're taking the cosine of the first angle times the cosine of the second one, then you're subtracting, and then you do the sine of the first one and the sine of the second one. It's important as you memorize these identities that you think about what they're telling you to do besides just memorizing the letters, because we will be working problems where this is not going to say A and B. It will have other things here, and we just need to know this structure so that we can rewrite this. Now, I've also got the cosine of a difference, A subtract B. You'll notice how very similar this second identity is to the first one. Cosine A, cosine B, sine A, sine B. All of that is exactly the same. The difference is the sign that goes between these. And I always want to associate that. Notice that when you're adding here, you're subtracting here, and vice versa. When you're subtracting here, you're adding here. So those have an opposite sign situation. Now, the first thing that we're going to do with these identities is we're going to use them to find the exact value of some angles that we've not been able to find exact values for in the past. Notice here we want to find the exact value of cosine 15 degrees. When we're asked for the exact value, we may not use a calculator answer. So what we're going to do here is we're going to think about writing this where we change that 15 degrees as either the sum or the difference of two angles. Now, what I like to do here is let's think about the special angles that we know. Of course, we know the trig function values of 45 degrees, don't we? We also know 30 degrees. We know 60 degrees. We know 90 degrees, of course 180 and 270 and so on, okay? What I want us to do is to look at this list of angles that we know exact values for and think about how can I produce 15 degrees by either adding or subtracting two of these. Well, as it turns out, I believe I can get 15 degrees two different ways. Notice that 45 subtract 30 would give me 15 degrees. So if I wanted to up here, I could put inside this parenthesis 45 degrees subtract 30 degrees, because in this parenthesis then, if I subtract those, I get this 15 degrees. Notice, however, that if I take 60 degrees and subtract 45, that would also be 15 degrees. So I could choose to use 60 subtract 45 here, and I should get exactly the same answer if I'm careful with my work. Now, having written this out, we're going to apply the identity that we just looked at. We have the cosine of the difference of two angles. So let's write that identity out. In fact, I encourage you, as you do your homework on this section, that every time you do this problem, if you will write out that identity, by the time you get through with your lesson, you will probably have the identity memorized. So we know that we're going to take the cosine of the first angle times the cosine of the second angle, and then remember it has the opposite sign of this, so that will be a plus. The sine of the first angle times the sine of the second angle. Okay? Now, we know the value of cosine 45 degrees, so we're going to replace that. The cosine of 45 degrees is the square root of 2 over 2. Notice that we're multiplying here times the cosine of 30 degrees. Well, the cosine of 30 degrees is the square root of 3 over 2. Then we have a plus sign. The sine of 45 degrees is the square root of 2 over 2 times the sine, oops, I wrote 15 there, that's 30 degrees. The sine of 30 degrees is 1/2, okay? Now, remember that when you have several operations, you follow the order of operations. So we multiply before we add, don't we? Well, the square root of 2 times the square root of 3 gives us the square root of 6. And of course, our denominator is 2 times 2 are 4. Plus, the square root of 2 times 1 is the square root of 2. And the denominator is, again, 4. Now, you'll notice we do have a common denominator, so we can add these fractions. However, remember, when you're working with radicals, in order to add two radicals, they have to be alike. The square root of 6 is not like the square root of 2. So that's like having two different variables. So the only way we can show that numerator is just to put the square root of 6 plus the square root of 2 and have that over 4. So part of what's going to be going on with you here is knowing your identity so that you can write this out, knowing the exact values so that you can replace these things, and then finally simplifying, which may require that you recall some things about working with radicals. Now, this second one is to find the exact value of the cosine of 165 degrees. Now let me put our angles back up here so that we can sort of look at them and think about how can we get 165 degrees. Now you can see if you add these, that's only 75. Of course, here's 105. 90 plus 45 is only 135. And of course 180 is more than that. So we may have to think about this a little bit and get a little bit creative when we try to come up with this 165. I have a suggestion here. Notice that if we take 180, that's more than 165. Okay, and so we could maybe subtract something from that. So let me start by saying, let's do the cosine. Let's put 180 degrees right here, and let's think about what would I have to subtract from 180 degrees to get 65 degrees? That would be 15 degrees, wouldn't it? Okay, well, do you see what I'm thinking? See, this 15 degrees, we just did that right up here, didn't we? So we can use that now that we have that up there. Okay, well, let's write out our identity. I think I'm going to come down a step so I have plenty of room. We have the cosine of 180 degrees times the cosine of 15 degrees. Now remember, when we're subtracting here, we add down here the sine of 180 degrees times the sine of 15 degrees. Okay? Now, let's think about 180 degrees. Now recall, 180 degrees is like pi. And again, I go to think about my graph. The cosine graph at pi is on -1, isn't it? So the cosine of 180 is -1. The cosine of 15 degrees we got right up here, the square root of 6 plus the square root of 2 over 4. And then what is the sine of 180 degrees, or pi, if you're thinking about it like that? At pi, the sine function is on 0, isn't it? This is 0 times the sine of 15 degrees. Well, of course, 0 times anything is just a 0, so that's going to be gone. And we just have -1 times this. So I'm just going to distribute my negative across that numerator, and we have the exact value of the cosine of 165 degrees. Okay, well, here we're asked for the exact value of the cosine of 105 degrees. Let me put this back up here. Remember, just a minute ago we were talking about, what if I add 60 and 45? That's 105, isn't it? So let's take this and write the cosine of 60 degrees plus 45 degrees, because that gives me my 105. Now we will apply our identity. Now we'll do the cosine of the first angle times the cosine of the second angle. Now remember, if you're adding here, this has the opposite sign. So subtract the sine of the first angle times the sine of the second angle. Okay, now we're ready to replace. What is the cosine of 60 degrees? Well, that's 1/2, isn't it? Times the cosine of 45 is square root 2 over 2. Subtract the sine of 60 degrees is the square root of 3 over 2. And the sine of 45 is 1/2. So now we will simplify. We have the square root of 2 over 4 minus the square root of, I'm sorry, I wrote something wrong right here. The sine of 60 is square root 3 over 2. The sine of 45 is square root 2 over 2. Said that wrong. Apologize for that. So I'm getting the square root of 6 over 4. I'm glad I caught that error. Now let's combine our fractions, since we have a common denominator of 4. But again, we can't actually subtract these radicals because they're different. So we'll just write the square root of 2 minus the square root of 6 divided by 4. Okay? You can see how important it is that you know these exact values of our special angles. If you're having to search for those, that's really going to slow you down as you work these problems. But if you've learned those really well, then you can just breeze right through here in terms of simplifying and substituting into this equation. Now here we're doing something similar. We're finding an exact value for a cosine, but you'll notice this time it's written in radians, 7 pi divided by 12. Let me put my list back up here that we've been working from. We know that 45 degrees is pi over 4, don't we? And 30 degrees is pi over 6. 60 degrees is pi over 3. I'm running out of space here, so I'm going to come on down. 90 degrees is pi over 2. Of course, 180 is pi. 270 is 3 pi over 2. So these are our special angles in radians, aren't there? What I suggest to my students is to think about this. We're trying to find the cosine of 7 pi over 12. And of course, we have all kinds of different denominators here. So it's sometimes helpful to convert each of these to a common denominator of 12. So we can look at this. So if I have pi over 4, if I multiply the numerator and denominator by 3, I get 3 pi over 12, don't I? Pi over 6, if I multiply the numerator and denominator by 2, I get 2 pi over 12. And this one I'll multiply both by 3, 4 pi over 12. And of course here I'd multiply by 6 pi over 12, and so on. But did you notice as I was rewriting these in terms of 12s, 3 pi over 12 plus 4 pi over 12 will give me 7 pi over 12, won't it? So what I'm going to do here is I'm going to write the cosine. I'm going to be adding these two to get my 7 pi over 12, but I'm going to write them in the familiar form that we know them as, pi over 4 plus pi over 3. Okay, so did you see how I decided how to use those particular angles? All right, now we will apply our identity. So we have the cosine of the first one times the cosine of the second one. Notice it's going to say subtract the sine of the first one times the sine of the second one. You'll notice how I'm saying that rather than using the A and B like we learned, because that tells me exactly what I'm going to do in this identity. Now, here we're doing the same thing we were doing a minute ago, but we're just thinking in radians instead of angles, or I'm sorry, instead of degrees. Pi over 4 is just like 45 degrees though, so we know the cosine is square root 2 over 2 times pi over 3. That's just like 60 degrees, isn't it? So the cosine of pi over 3 would be 1/2. Subtract. The sine of pi over 4 is square root 2 over 2. And the sine of pi over 3 is going to be square root 3 over 2. So simplifying again, we have square root 2 over 4 minus square root 6 over 4. You can see we're very often getting these same sorts of values here because we're working over and over with our special angles. Okay? Okay, I have one other of these that we're going to work with the exact value. This time we're trying to find the exact value of the cosine of negative 5 pi over 12. Well, let's look up here and let's think about how could we get negative 5 pi over 12. Looking at these, I don't see how we can subtract any of these and get negative 5 pi over 12, do you? Even if you think pi here is 12 pi over 12, see, we would have to work with that one. What I'm thinking about doing here is I can see that 3 pi over 12 plus 2 pi over 12 is 5 pi over 12. What if I just make those both negative? Let's look at that. Let's write this as the cosine. If I think negative 3 pi over 12, that's negative pi over 4. And I'm going to put then minus pi over 6. Okay? So there's my minus 3 pi over 12, and my minus 2 pi over 12 is my minus 5 pi over 12. Now, the way that we approach this, we can think about this two different ways. I think what I'm going to look at is this. My first angle is going to be a negative angle, but I'm going to look at this as a subtract sign as we write this identity out. So we have the cosine of negative pi over 4, that's my first one, times the cosine of my second angle is pi over 6. Now remember, I'm reading this as a subtract sign, so I'm subtracting two angles, which says here I'm going to add, right? And then I will do the sine of my first angle, negative pi over 4, times the sine of my second angle, pi over 6. Okay? Now, let's think about this cosine of negative pi over 4. This is just going to put me down in the fourth quadrant, but the cosine in the fourth quadrant is still positive, isn't it? So that's still going to be square root 2 over 2. And the cosine of pi over 6, of course, pi over 6 is just like 30 degrees, so the cosine of that is square root 3 over 2, plus the sine of negative pi over 4. Well, this is in the fourth quadrant, and we know in the fourth quadrant the sine value is negative. So that's going to be negative square root 2 over 2 times the sine of pi over 6, or 30 degrees, is 1/2. So we have the square root of 6 over 4 plus negative square root 2 over 4. We can write that as the square root of 6 minus the square root of 2, all divided by 4. I hope that at this point you've seen how we are using these identities over and over, the same identity, and I hope by now, even with just these few problems that we've already worked, perhaps you're already beginning to memorize these particular identities. Now, in these next few problems, we're going to be asked to simplify something, and so we're going to see how we can use these identities to simplify expressions. Simplify the cosine of 82 degrees times the cosine of 98 degrees minus the sine of 82 degrees times the sine of 98 degrees. Now, guys, the key here is to realize you're doing cosine, cosine, subtract, sine, sine. Notice these are the same and these are the same. So it's like the cosine of the first one times the cosine of the second one minus the sine of the first one times the sine of the second one. That's our identity, isn't it? So we know that we're doing a cosine here, and since this says subtract right here, what are we doing with these angles? We're adding them, aren't we? 82 degrees plus 98 degrees. Do you see how this identity would be written like this? Okay? So now what we're going to do is to actually go ahead, since we have those inside that parenthesis, and add those. Well, let's see, we've got a 10 there. 10, 18, that's 180 degrees, isn't it? Well, what is the cosine of 180 degrees? It's -1, isn't it? So see how nicely that expression simplified all the way down to just the single number, -1. We have another one here that we want to simplify. The cosine of 11 pi over 12 times the cosine of pi over 4 plus the sine of 11 pi over 12 times the sine of pi over 4. Look again at your structure. Cosine times cosine plus sine times sine. These are the same. These are the same. So again, this fits our identity, doesn't it? Cosine, our first angle is 11 pi over 12. Now what are we doing? Adding or subtracting? Since this says add here, we know we are subtracting here, aren't we? Pi over 4. So in order to subtract these, we need a common denominator in here. So let's rewrite the 11 pi over 12. We'll multiply numerator and denominator by 3 here to change that to 3 pi over 12. And then when we subtract, 11 pi subtract 3 pi is 8 pi over 12. We can reduce 8 pi over 12, can't we? So let's divide by 4. That will give us a 2 pi in the numerator and a 3 in the denominator. Now, we don't want to stop yet, because let's think about this 2 pi over 3. That's one of our special values that we're going to know. 2 pi over 3 is simply going to take us over here to the second quadrant, and our reference angle is going to be pi over 3, or 60 degrees. So we know that numerically this has the same value as the cosine of pi over 3, but since we're in the second quadrant, that cosine value will be negative. So our value here is just going to be -1/2. Okay, on this next problem that we're going to simplify, you'll notice that it says find the cosine of the quantity 3 pi over 2 subtract theta. Now how are we going to simplify this? Well, let's see. We are subtracting two things inside this parenthesis, and we're doing a cosine. So our identity would apply here. Let's write that out and see what happens. I'll take the cosine of our first one, 3 pi over 2, times the cosine of our second one, theta. Now since this says subtract, I'll be adding the sine of the first one, 3 pi over 2, times the sine of the second one, theta. Now, these we know some values for, don't we? Let's think about 3 pi over 2. What is your cosine graph doing when x is 3 pi over 2? It's on 0, isn't it? So we have 0 times the cosine of theta plus. What about your sine function at 3 pi over 2? If you think about your sine graph, you know that at 3 pi over 2, your sine value is -1 times the sine of theta. So of course 0 times anything is 0, and so we just have a -1 times sine theta, or minus sine theta. Okay? So we have simplified. Notice that this is much simpler than having this complicated argument of our cosine function here. Okay? Now what we've seen so far is how we can use these addition and subtraction formulas for the cosine function to find exact values of angles that we couldn't do before. We've also seen how that we can simplify some expressions using these identities. And as it turns out, there's also some new identities that can be proven from these sum and difference identities. These are called the cofunction identities. Now let's take a look at those identities. The cofunction identities. Notice it says the cosine of 90 degrees subtract theta is equal to the sine of theta. Have you ever wondered why we say sine and cosine? That's because those are cofunctions. The sine and cosine are called cofunctions. Notice here the sine of 90 degrees minus theta is equal to the cosine of theta. Sine and cosine. What is the relationship, though, among these arguments? Well, let's think about this. If I take 90 degrees and subtract theta, if theta is an acute angle, I'm finding the complement of angle theta, right? Complementary angles add up to 90 degrees. So we're seeing here that if I have complementary angles, angles that add up to 90, the sine value and the cosine value will be equal. Okay? Now, tangent and cotangent are cofunctions, so the tangent of 90 degrees minus theta equals the cotangent of theta, or vice versa. The cotangent of 90 degrees minus theta equals the tangent of theta. And then, of course, we have secant and what? Cosecant. Okay, so secant and cosecant will be equal, again, if these angles are complementary. In other words, they add up to 90 degrees. Now, a couple of comments. First of all, 90 degrees can be replaced by pi over 2. So if you're working in radians, this is just going to say pi over 2 minus theta here. But the other interesting thing is theta can be any angle. Now, when I was talking to you up here, I said, suppose theta is an acute angle, then we're doing complementary angles. It turns out that theta does not have to be an acute angle. It can be any angle. So the key is that if I take this angle here, okay, and what's over here, 90 minus theta plus theta is 90 degrees. So the angle here plus the angle here will add up to 90 degrees, okay? Now, what I want to do is to take this first one, the cosine of 90 degrees minus theta, and we're actually going to verify this first identity here. The identity we just learned when we're subtracting in here is to take the cosine of the first one times the cosine of the second one, and then we do what? We add the sine of the first one times the sine of the second one. Well, what is the cosine of 90 degrees? It's 0. So I have 0 times cosine theta. What's the sine of 90 degrees? It's 1. So I have 1 times sine theta. And of course you can see then that we are getting, oops, I just can't write, can I? Sine theta over here. So we've actually verified this first identity here. We're not going to verify the others, but what we want to talk about is how do we use these cofunction identities as we're doing problems. First of all, remember cofunctions, sine, cosine, tangent, cotangent, secant, cosecant. Those are cofunctions. And we're saying a sine will equal a cosine if their arguments add up to 90 degrees, or pi over 2 if you prefer. A tangent will equal a cotangent, again, if their arguments add up to 90. A secant will be equal to a cosecant if their arguments add up to 90. Okay? So let's go to a problem now and see how we can use these cofunction identities. Here we're instructed just to fill in the blank to make a true statement. Notice here I have sine 15 degrees. I want it equal to a cosine. Sine, cosine, these are cofunctions. When will cofunctions be equal? If these arguments add up to 90. So if I take 90 degrees and subtract 15 degrees, That's 75 degrees, isn't it? So if I put 75 degrees here, the sine value of 15 will equal the cosine value of 75. Cofunctions, these angles add up to 90. Okay? Now let's look at this one. I have a tangent of 5 pi over 8. I want it equal to a cotangent. Tangent, cotangent. So what has to be true about these arguments? Well, they have to add up to 90 degrees, but since this is in radians, 90 degrees is saying what? Pi over 2. So if I take pi over 2 and I subtract this 5 pi over 8, I'll get what I need over here. Well, let's change this. Pi over 2 is 4 pi over 8 multiplying by 4 minus 5 pi over 8. Notice that gives me a what? A negative pi over 8. Okay? Well, notice I have cofunctions here. If I add these, I get 4 pi over 8, which reduces to pi over 2. So those have to add up to pi over 2. Well, let's look at this one. I have a cosine and a sine again. This is cosine 132.51 degrees equals a sine. Well, these have to add up to 90 degrees. So if I take 90 degrees, oops, I forgot my 0, 90 degrees, and I subtract 132.51 degrees, let's see what we get. I'm just going to use my calculator here. 90 subtract 132.51 gives me a negative 42.51. Okay? So if we look at this, we have cofunctions. Do these add up to 90 degrees? Well, notice they have opposite signs. When you have opposite signs, you actually find the difference, don't you? So the 51s would cancel out. The 2 would produce a 0. If we subtract 4 from 13, we get 90, don't we? So those will add up to 90. So do you see how we're using the cofunction identities? Sine, cosine, these add up to 90. So if you know one, subtract it from 90. Tangent, cotangent, these are cofunctions. Since we're working in radians, these have to add up to pi over 2. So if I take pi over 2 and subtract the one I know, I get the other one. Again, sine and cosine, these have to add up to 90. So if I take 90, subtract the one I know, then I find the other one. Well, we have some more blanks to fill in on this one. Here we're doing secant and cosecant. These are cofunctions. So what about these? They have to do what? They have to add up to 90. So I need 90 degrees, subtract 58 degrees 29 minutes to find my other angle. Remember how to do this? Let's rewrite this 90 degrees as 89 degrees 60 minutes. We're subtracting 58 degrees 29 minutes, aren't we? So if we subtract the minutes from the minutes, that's 41. No, 31. I need my calculator, don't I? Let me just start that over right here. 31 minutes, okay? Let's double check that. And then if I subtract 58 from 89, that one's going to be easier. 31 degrees there. That's interesting. 31 degrees, 31 minutes. Well, let's double check this. If I add 29 minutes and 31 minutes, I get 60 minutes, right? So that would make this, adding these, I get 89 plus the 1 would be 90. So we're okay there. 31 degrees, 31 minutes. Okay? Okay, on this last one, I have a cotangent and a tangent here, don't I? These are cofunctions. So what do I know about these? Well, let's be real careful here. Notice there's no degree symbol on this 2.134. This is not degrees. It would have to have a degree symbol. So this must mean it's radians, but it's not in the pi form of radians. So let's think. It has to add up to pi over 2, so I need pi over 2 subtract 2.134. Well, how am I going to do that? Well, I'm just going to go to my calculator. We all have a pi button on our calculators, don't we? So I'm going to get my pi, 3.14159, etc., divide by 2. And so I'm just going to write part of this. This is sort of like 1.57079. There's some more decimal places there that I'm showing you my calculator. I'm going to subtract from that 2.134. Okay, and since we've got this rounded off here, And we'll have to do the same thing here. We've got a negative 0.563 here, okay? Now these will sort of be approximately equal. They might not be perfect because we've had to round off here, but do you see how that same thing is working? These need to add up to pi over 2. So I can do this with my calculator. Pi divided by 2, subtract this other number over here. If you add these, you should get very close to this 1.57 stuff that we have right here. Won't be perfect because we've had to round off on this one. Okay, here we're still filling in blanks. Fill in the blank to make a true statement. Tangent 24 degrees equals 1 over something 66 degrees. Well, let's take a look at this. 66 degrees and 24 degrees, doesn't that add up to 90? It does, doesn't it? Well, let me think. I know that the tangent then of 24 degrees would equal the cotangent of 66 degrees. Using my cofunction identities, cofunctions, these add up to 90. But what I have here is 1 over something. Well, the cotangent is equal to what? 1 over the tangent. So do you see how we're sort of thinking through this one? This needs to say tangent down here because it's in the denominator. 1 over tangent 66 is the same thing as cotangent 66. That's equivalent to my tangent of 24. Okay? All right, on this one we have the sine of 2 pi over 3 equals something negative pi over 6. Well, let's see. If I'm going to put a cofunction here, these have to do what? They have to add up to pi over 2 or 90. Let's see if they do. 2 pi over 3 and a minus pi over 6. Let's get a common denominator. If I multiply these by 2's, I get 4 pi over 6 minus pi over 6, which is 3 pi over 6, and that does reduce to pi over 2, doesn't it? So these add up to pi over 2, which says these need to be cofunctions. What's the cofunction of sine? It's cosine. So cosine goes in this blank. Now I wanted to put this one on here to sort of caution you about something here. These look almost the same, but you'll notice the difference here. These numbers are different, whereas here these numbers are the same. Because I want to point out that sometimes students get confused. Remember that tangent and cotangent are cofunctions, but they are also reciprocals, aren't they, of each other? Let's look at those identities. We have that the tangent of 90 degrees minus theta equals the cotangent of theta, or the cotangent of 90 degrees minus theta equals the tangent of theta. When we're doing cofunctions, these arguments have to add up to 90 degrees or pi over 2. But your reciprocal identity looks like this. Tangent theta equals 1 over cotangent what? Theta. Notice these are the same. Cotangent theta equals 1 over tangent what? Theta. These are the same. So when you're doing reciprocals, your argument or angle stays the same. If you're doing cofunctions, then the arguments add up to 90. Well, let's look at this one. Here, notice the arguments are the same, 57 degrees. So we're using the reciprocal. This is cotangent here. If these arguments are the same, we're using reciprocals. But notice here, 57 degrees plus 33 degrees adds up to 90 degrees. Well, we know that the tangent of 57 degrees will equal the cotangent of 33 degrees. Cofunctions, these add up to 90. Since I'm writing 1 over, this is like the problem we did a while ago. Cotangent 33 is the same as 1 over tangent 33. So be very careful when you're working with this tangent and cotangent. Decide, are you doing a reciprocal identity or are you using that cofunction identity? You shouldn't have that problem with any of the others because remember, secant is the reciprocal of cosine, but the cofunction of secant is cosecant. So those we can keep straight. Okay, In this next problem, we're asked to find a value of theta that will make a true statement. We want this to be true. Notice here we have cofunctions, sine and cosine. So whenever we have cofunctions, these have to do what? They have to add up to 90. So I'm going to take the theta over here plus the 2 theta minus 10 degrees over here. This has to equal 90 degrees for these to be for this to be a true statement. If I have sine and cosine equal to each other, these arguments have to add up to 90. So I'm just going to show that. They add up to 90 degrees. So let's solve for theta now. Theta plus 2 theta is 3 theta minus 10 degrees equals 90 degrees. We'll add 10 degrees over here, so 3 theta is 100 degrees. And then we will divide by 3. 100 degrees divided by 3. Of course, that doesn't divide evenly, but that does give us the exact value of theta that would make this a true statement. Okay? This problem is similar. Find a value of theta that will make a true statement. Notice you have what here? Cofunctions, cotangent and tangent. So if we have cofunctions here, what has to be true about these arguments? That's right, they have to add up to 90 degrees. So theta minus 10 degrees plus 2 theta plus 20 degrees has to add up to 90 degrees. Okay, well let's simplify. We have 3 theta plus 10 degrees equals 90 degrees. This looks familiar. Subtract 10 degrees. Well, it's not quite the same because here we're subtracting that 10 degrees instead of adding it, so we get 80 degrees. And then again, we'll divide by 3. Well, once again, this doesn't divide evenly, but it does give us the exact value of theta that we need to have a true statement. Notice how we're just using the fact that when we have cofunctions, their arguments have to add up to 90 degrees. Or if you were doing radians, then they would add up to pi over 2. In these next few problems, we're going to see how we can evaluate the cosine of a sum or a difference based on given information. So let's take a look at those. We are to find the cosine of x plus y and the cosine of x minus y, given that the sine of x is 2/3, x is in quadrant 2, the sine of y is negative 1/3, and y is in quadrant 4. Well, let's start with what we were asked to find. We're asked to find, first of all, the cosine of x plus y. So we know from our identity that we take the cosine of the first one times the cosine of the second one. Since we're adding here, we will subtract the sine of the first one times the sine of the second one. Now, we need to replace these. Do we know the cosine of x? No, we don't. We're given the sine of x and the sine of y, but we're not given the cosine of x. So we're going to do a little work here to find that. Now, you might recall that there's more than one way to find those values. On this first one, I'm going to use sort of the triangle idea. X is in quadrant 2. So we're going to go over here to quadrant 2. Of course, our angle X is here, but we're going to drop a perpendicular down here to this side right here. Now, our sine value is 2/3, okay? And remember, the sine is opposite over hypotenuse, or if you think sine is y over x, this y value is 2, and our r value is 3. I think I said y over x, y over r, okay? So then, can we use this right triangle here to find our x value that goes here? Now, don't be confusing the x value here with x, which is our angle. So I'm speaking in terms of coordinates now. We know that if we take this value and square it plus the 2 and square it, it equals 3 squared. So we can take 9 and subtract 4, which gives us 5. So this side has to be the square root of 5, doesn't it? Notice 4 plus 5 is 9, which is 3 squared. Notice this needs to be the negative square root of 5 since we're over here on this side of our origin. And so we can look at this and we know then that the cosine of this angle is going to be this value over our r, negative square root 5 over 3 is our cosine value. Now, we also need the cosine of y here. We're going to be multiplying. We are given the sine of y, but not the cosine. So I'm going to do this one a slightly different technique. I'm going to use identities. We know sine squared x plus, let's use y here. We're looking for cosine of y. Sine squared y plus cosine squared y equals 1, doesn't it? We're given that the sine of y is negative 1/3. So if I square that, I get 1/9. 1/9 plus cosine squared y equals 1. Let's subtract that 1/9 from 1. Cosine squared y then will be 8/9. And we know we need to take a square root to get our cosine. Well, let's think. Y is in quadrant 4. In quadrant 4, the cosine is positive, so we'll take the positive square root of 8/9. Of course, the square root of 8, we can write 2 square root 2, and the square root of 9 is 3. So the cosine of y is 2 times the square root of 2 over 3 here. Okay? Now, we will subtract. The sine of x was given up here as 2/3 times the sine of y is negative 1/3. So we've replaced each of these 4 values. Now let's simplify. Notice you're multiplying a negative times a positive. So we're going to have 2 times the square root of 10, which is negative, over 9. Subtract. Here again we're multiplying a positive times a negative, so that's a negative 2 over 9. Of course, minus a negative is going to be plus a positive. So let's write this as negative 2 square root 10 plus 2 all divided by 9. Of course, if you prefer, you could put 2 subtract that, couldn't you? Okay? Now, we have done the cosine of x plus y. We're also asked to do the cosine of x minus y. Well, we've already done most of the work. Our identity, of course, starts out the same. Cosine x, cosine y, but here we'll have a plus sign. Sine x, sine y. So we're going to be using these same values, but we'll just be adding here. So I'm just going to go ahead and multiply these. We have negative 2 square root 10 over 9. This is going to change to a plus the negative 2 over 9. And so when we combine these, we have negative 2 square root 10 minus 2 all divided by 9. So you can see that once we had found one of these, the other one is real easy. It's just a matter of changing from subtract to add. Now, in terms of finding these missing values, it really doesn't matter which technique you use as long as you are finding one that you're comfortable with. And the most important thing here is that whichever technique you use, you have to be careful of your quadrants so that you get the correct sign on each of these. Okay, I've got another one of these that we're going to do which is similar to this. Again, we're asked to find the cosine of x plus y and the cosine of x minus y. This time we're given that the cosine of x is square root 2 over 4. X is between, notice, 3 pi over 2 and 2 pi. What does that tell you? Between 3 pi over 2 and 2 pi is saying what? We're in quadrant 4, aren't we? The sine of y is negative square root 5 over 6, and notice where y is. It's between pi and 3 pi over 2. Where does that put y? It puts it in quadrant 3, doesn't it? Okay? Alright, so again, let's start with cosine x plus y. Our identity says cosine x times cosine y, subtract sine x, sine y. Now let's start replacing. Do we know the cosine of x? Well, yes, we do. They gave that to us. So we're going to have square root 2 over 4 here, times. Do we know the cosine of y? No, he gave us the sine value, so we're going to have to calculate the cosine value. So let's see. Maybe I can do it right here. I've got space. Y we decided was over here in quadrant 3. Okay? And so if the sine is negative square root 5 over 6, we would label our triangle like that. Opposite over hypotenuse. And then to find this value, we would have 36 subtract 5, let's see, is 31. So this side would be square root 31, and it would be negative, wouldn't it? Okay, let's check that. The square root of negative square root 31 squared is 31. We square this, we get a positive 5. If we add those, we get 36, which is 6 squared. So we're okay here, aren't we? So the cosine of y is going to be negative square root 31 over 6. Then we're subtracting the sine of x. No, we don't have that, so we're going to calculate that one. Shall we do that one with identities just to be different here? Let's see, sine squared x plus cosine squared x equals 1. So we have sine squared x plus, let's see, if we square this cosine, we get a 2 over 16, don't we? 2 over 16, I'm going to go ahead and reduce that to 1/8. Did you follow that? If we square this, we get 2 and 16, which reduces to 1/8, equals 1. So sine squared x, if I subtract 1/8 from 1, I have 7/8. We need to take a square root. Now, which quadrant are we in for x? X is in quadrant 4. Our sine value in quadrant 4 is negative, so we need the negative square root. Square root 7 over 2 square root 2, and let's rationalize that thing. If we multiply by the square root of 2, we get negative square root 14 over 2 times 2 is 4. Okay? So our sine of x is negative square root 14 over 4 times the sine of y was given as negative square root 5 over 6. Okay, now let's simplify. Here I have a positive times a negative, so this is minus the square root of 62 over 24. Subtract. Notice here you're multiplying two negatives, so that's going to be a positive. Let's see, 5 times 14 is square root 70 over 24. So we have minus the square root of 62 minus the square root of 70, all divided by 24. Okay, so we've got the first part. Now let's do the cosine of x minus y. Cosine x minus y is the cosine of x times the cosine of y plus the sine of x times the sine of y. So if we'll just go back down here, everything's going to be the same, except we will be adding. Okay? And so then we can simplify this to negative square root 62 over 24. I'm sorry, negative square root 62 plus square root 70, all divided by 24. Okay? So you want to write out your identity, and then you are going to replace each of these. Sometimes the information will already be given. If it's not, then you have to find that information, and that goes back to the first part of your trig class, where you learn to use one value of a trig function to find another missing value. Now, the last couple of problems that I want us to look at in this lesson are to verify some identities. And we will be using this new identity that we've learned here to verify some identities. Cosine x plus y plus the cosine of x minus y, we're saying, does this equal 2 times the cosine of x times the cosine of y? Remember, when you're verifying identities, you can only work on one side of the equation. So let's take this left-hand side, and the reason I'm choosing that is because I see these forms involving these identities that we've been learning, and I know I can rewrite those. So here we have the cosine of x times the cosine of y, subtract the sine of x times the sine of y, and then we're adding. We'll use the identity for this one, the cosine of x times the cosine of y. Notice add the sine of x times the sine of y. Now, do you notice these two terms? Those are opposites, so they're going to drop out, aren't they? Look at these two. They're just alike, so we can add them together. And we have 2 cosine x cosine y, which verifies our identity here. Notice that was just a simple matter of using our identities for the sum and the difference and then just simplifying. Verify the identity. Cosine pi over 2 plus x subtract y equals the sine of y minus x. Now this one looks really different. We're wanting to show that this is true, and I think I'm going to start on this side because this is certainly more complicated in here than this is here, and we'll see what happens. Now I'm going to do a little bit of rewriting here to do this. I'm going to write pi over 2 sort of by itself, and then I'm going to group this x minus y thing right here. The reason I'm doing that is because our identity talked about how to do the cosine of a sum of 2 things, not when we're doing 3. So we're going to, for right now, treat this as just one angle. So let's use our identity. We have the cosine of pi over 2 times the cosine of this x minus y thing. Since we're adding here, this will be a subtract. The sine of my first one, pi over 2, times the sine of my second one, x minus y. Okay? Now, what do we know about the cosine of pi over 2? That's 0, isn't it? So I have 0 times the cosine of x minus y, subtract. What is the sine of pi over 2? It's a 1 times the sine of x minus y. Now, the 0 times anything is 0, so that's gone. So we have minus the sine of x minus y. Now let's look at what we were trying to get. We were trying to get the sine of y minus x. It does not have a negative out here, and notice how it's turned around. Oh, well, let's think a minute. Remember this identity? The sine of negative theta equals what? Minus the sine of theta. So what I can do to get rid of the negative out here is change the sign on what's in here. So this is equal to the sine of the negative of x minus y. And notice if you distribute that negative, you're going to get a minus x and a plus y. So I'm going to write the plus y first. And we have verified our identity. So first of all, we did some grouping here so we could use our cosine of a sum. We evaluated the cosine and sine of pi over 2. And then when we got here, we recalled our negative angle identities to be able to simplify and get to the form that we were trying to prove here. This concludes our lesson on sum and difference identities for the cosine function. You'll need to memorize these identities if you haven't already. Be sure you work on the form of what they're saying. The cosine of the first one times the cosine of the second one, and then you'll either add or subtract the sine of the first one times the sine of the second one. And remember, whether you add or subtract, that's always the opposite of what you're doing inside that parenthesis on that first part. This concludes this lesson. I hope that you found it beneficial.